Hi everybody, I hope this video finds you well. In today's video, we're going to be starting into section 9.4 from your textbook, which introduces us to a sort of more general method for solving a special type of linear system of differential equations. Just like in chapter 8, the sort of first type of equation that we dealt with was the constant coefficient higher order linear differential equation. So the first type of linear system that we're going to be working with is also a constant coefficient system. So we'll define what a constant coefficient system is, talk about sort of a observation or main idea, state a theorem that tells us what to expect in general for these types of systems, and then look at a couple of examples of this. So let's get into talking about this definition here. So this definition says a linear system of differential equations is called a constant coefficient system if that a of t is actually a matrix of constants. So instead of being a function of t, you could just call it a matrix A. So in other words, when we have a vector differential equation, if that a of t is just a set of constants, so just a normal matrix A rather than a set of a matrix of functions, then we would call it a constant coefficient system. The observation or main idea for solving these is something we hinted at back when we took our look at our first example of solving a system back in section 9.1. It's going to relate to the concept of eigenvalues and eigenvectors. So suppose we have a homogeneous constant coefficient vector differential equation, which you can write sort of in general as x prime of t equals ax of t. Now notice I don't have to write a of t because we're assuming that it's constant coefficient. So this matrix A is just constant functions. It's just a matrix of scalars. So we're going to further suppose that lambda is an eigenvalue of A with corresponding eigenvector V. Now, it's been a little while since we talked about eigenvalues and eigenvectors. So remember what this actually means is that if we do matrix multiplication of A times the vector V, then it's the same as scalar multiplication of that vector by that lambda. So when you say that you're supposing that lambda is an eigenvalue of A with corresponding eigenvector V, what we're really saying is that AV equals lambda V. Now we're going to consider the vector function x of t equals e lambda t times that eigenvector v. And our claim or our observation is that a function of this form is actually a solution to the above vector differential equation. So to actually support this observation, let's actually confirm this. So let's confirm this observation. So how are we going to sort of confirm that? Well, we'll go ahead and we'll actually verify by left-hand side, right-hand side approach that these two things are equivalent. So we're saying that x of t is going to be e lambda t times v. So let's look at our left-hand side. Our left-hand side is going to be x prime of t. What can we say about that? Well, if we're differentiating this x of t here, we're going to be differentiating this. Obviously, this is the part that we'd be differentiating because we're differentiating with respect to t. V is just a vector there. So that would become lambda e lambda t v. That's what our left-hand side looks like. All right, now let's talk about our right-hand side. For the right-hand side, we're going to have that axt. So ax of t. But of course, this x of t is this e lambda t v. So we can actually say this is a e lambda t v. Now, we can do a little bit of manipulation. This e lambda t, it's a scalar function. It's a function, but it is a scalar. It's not a matrix or a vector or anything like that. So we can just scoot that into the front there. So this is e lambda t a v. And remember our assumption that v is an eigenvector with corresponding eigenvalue, lambda. In other words, like we said here, AV is lambda v. So we can replace this, there we go, with e lambda t lambda v. And again, that's because that's the definition of eigenvector. All right, and then of course, this guy here, that lambda, also a scalar. This is a scalar function. Might as well just put that lambda in front. So we get lambda e lambda t v. What do we notice here? This guy, absolutely the same. So this right here, this right, oh, that looks terrible. That right there, these guys here, the same. Check. So this shows us that in this situation, where we have an eigenvalue and corresponding eigenvector, we know how to determine at least one solution to the vector differential equation. Now, this obviously is just a first step. We're only determining a single solution here, but consider what we did in the previous video. We stated some results that if we're looking at a homogeneous linear system of differential equations, we know that it's going to be a vector space or a subspace of dimension n, meaning that if we can find n linearly independent functions in this form, then we can go ahead and say that every solution will be a linear combination of those n linearly independent vector functions. So even though this is only saying that this is one single solution, well, we know that often a matrix has several different eigenvalues or several different corresponding eigenvectors. So even though this is just a single observation so far, it's going to really be the foundational sort of building block. Okay. So let's go on and talk a little bit more about how we're going to apply this in general. Now that we have this observation that this type of vector function, x of t equals e lambda t of v times v, is going to be a solution to the constant coefficient homogeneous system of linear differential equations. Okay, so let's recall this definition real quick. This is something that we did back in chapter 7. This was something that when we were talking just about eigenvalues and eigenvectors in general. So remember that a square n by n matrix is called non-defective if the matrix has n linearly independent eigenvectors. So remember, some matrices are non-defective, some are defective. Right now, in this section 9.4, we're going to focus on ones that are non-defective. In other words, matrices that have n linearly independent eigenvectors. Actually, from our observation on the previous slide and this statement and this sort of definition here, we should pretty much already know what we're going to be saying here, right? We needed n linearly independent functions to find a basis for the overall solution space. And now we just said that if you're non-defective, you have n linearly independent eigenvectors. So for those n linearly independent eigenvectors, we can use functions of this form, and that's going to be our basis for the solution space for the homogeneous system. So that's exactly what this theorem says here. So let's consider the constant coefficient homogeneous vector differential equation, x prime of t equals ax of t. Again, we're just saying a here is constant coefficient. Furthermore, for this theorem, and again for the remainder of section 9.4, we'll deal with defective in 9.5, but let's suppose that matrix A is non-defective, so it has n linearly independent eigenvectors. So in other words, we're going to suppose that matrix A has n linearly independent eigenvectors, v1 through vn, with corresponding eigenvalues lambda 1 through lambda n. Now, I do want to make a note here. While we are under the assumption that v1 through vn are linearly independent eigenvectors, remember, sometimes a single eigenvalue can have several linearly independent eigenvectors. So this lambda 1 through lambda n, each of these correspond to these eigenvectors, but these eigenvalues may not be distinct. So in other words, v1 and v2 might be linearly independent, but lambda 1 and lambda 2 might be the same because v1 and v2 are actually two linearly independent eigenvectors for the same eigenvalue. Remember, the potential for several linearly independent eigenvectors for the same eigenvalue happens when that eigenvalue has multiplicity greater than 1. And we'll see some examples of that. Then, the statement of this theorem is that the general solution to this vector differential equation is a linear combination of solutions of the form from the previous slide. So, x of t is c1 e lambda 1 t v1 plus c2 e lambda t v2 plus cn e lambda n t. You'll notice that this is a vector function, even though the c k e lambda k t, that's a scalar function, but it's made into a vector function by that multiplication on to those eigenvectors. So we're going to prove this. How are we going to prove this? Well, we already know from our work in section 9.3, from section 9.3, we know the solution space to x prime of t equals ax of t will have, I guess is a better way of phrasing that, will have dimension n. So we already know that this guy will have dimension n. So all we need to do is to make sure that each of these guys actually is linearly independent. Then we'll have linearly independent functions, and we'll have n of them. So since we know the dimension is n, that will definitely form a basis. So you might say, don't we already know that they're linearly independent? Well, we almost do. We know that these eigenvectors are linearly independent. We need to show that these functions are linearly independent. So we know v1, v2 through vn are linearly independent. What we need to show is we need to show that the functions e lambda 1 t v1, e lambda 2 t v2, e lambda n t vn are linearly independent. And just to help you guys understand why we actually need to show this, I'm just going to put here, I mean, when we say linearly independent, we mean linearly independent. But notice that this would be linearly independent in Rn. V1 through Vn are just n-dimensional vectors. But these guys would be linearly independent in Vn of R, the space of n-dimensional vector functions. So we know the eigenvectors are linearly independent, but we need to show that these vector functions are also linearly independent. Well, how do we show linear independence of things in Vn? Well, we use this new Wronskian that we talked about. So what does the Wronskian of this guy look like? Well, the Wronskian of e lambda 1 t v1, comma e lambda 2 t v2, comma e lambda n t vn. Well, it would be the determinant of the matrix that has these as its columns. So e lambda 1 t v1, e lambda 2 t v2, e lambda n t vn. Now again, these guys here, these are scalars, but v1, v2 through vn, those are column vectors. Now remember though, we learned some things about determinants. We learned that if you multiply a row or a column by a scalar, then you can factor that out, right? Or you change the determinant by that same scalar amount, right? If you multiply a row by 2, then you multiply its determinant by 2. So in other words, we can factor out scalars from a determinant. So we can actually factor these scalar functions out of the determinant. So this then becomes e lambda 1t, e lambda 2t, e lambda nt times the determinant of the matrix v1, v2 down to vn. Now this determinant here is a determinant just of scalar valued vectors, right? There's no functions left in here. Everything in here would just be numbers at this point. All right, now things are pretty much done here. We can see that this is just going to be e lambda 1 plus lambda 2 plus lambda n t times this, v1, v2, vn. And, of course, the exponential here, that's never going to be 0. And this determinant can't be 0 since v1 through vn are linearly independent. Since they're linearly independent, right, if we did c1 v1 plus c2 v2 plus cn vn equals 0, then we know that there would be a unique solution, only c1 equals c2 equals cn equals 0, which means that the matrix has to be invertible, which means it has to have full rank, so this determinant must be non-zero, right? This is not equal to 0, since e lambda 1 plus lambda 2 plus lambda nt is not going to be 0, and this v1, v2, vn determinant is not going to be 0, v1, vn, linearly independent. So that shows that the Wronskian of these n vector functions is non-zero. From our previous work in section 9.3, we know that if the Wronskian is non-zero, that tells us that these functions are linearly independent in Vn of R, and there we go. So I'm just going to go tuck this in here, even though it's a little bit weird, just so we don't move on to a different page. Since Wronskian not equal to 0, functions, vector functions are linearly independent. So since we have n linearly independent vector functions, they must form a basis since dimension equals n. And that goes back to what we did all the way back in chapter 4, where we said if you have a number of vectors equal to the dimension, then being linearly independent is equivalent to being spanning, is equivalent to being a basis. So since we already know the dimension here is going to be n, we just showed that our n functions are linearly independent. That guarantees that they'll also be spanning. It guarantees that they're a basis. There we go. We've now proved our theorem there. Check. All right, so just to recap here, what this theorem basically tells us is if we can figure out n linearly independent eigenvectors, which is not always possible, right? There are defective matrices out there, but for a non-defective matrix, you can figure out n linearly independent eigenvectors, then take each of their corresponding eigenvalues, construct these vector functions that are of the form e to the eigenvalue times t times the eigenvector, and then a linear combination of those vector functions will give us the general solution. Let's go ahead then and jump into some examples of doing this. All right, so here's a constant coefficient linear system of differential equations that's homogeneous. X1 prime equals 2x1 plus 5x2. X2 prime equals 3x1 plus, there's a little typo there. That should say 4x2. My bad there, excuse me. All right, so there we go. Now, again, notationally, this is a little bit of condensed notation. All of this stuff is actually hiding that these are x1 prime of t equals 2x1 of t plus 5x2 of t, etc., right? But that is just assumed that when we state these things, we don't have to show that of t there. Can we rewrite this into sort of our vector differential equation form? Yep, we can call this x prime of t is actually equal to the matrix 2, 5, 3, 4 times x of t, right? So that would be the sort of corresponding way of viewing it as a vector differential equation. All right, from the previous theorem, first thing we need to do is determine the eigenvalues of this. So we need to determine eigenvalues. So how do we do that? Well, we take the determinant of a minus lambda I. Remember that the eigenvalues are the solutions to the determinant of a minus lambda I equals 0. So we need to take, we can just skip the step of writing determinant. We can say 2 minus lambda, 5, 3, 4 minus lambda needs to equal 0. So we take a minus lambda I, which is subtracting lambda off the diagonals, take the determinant, set it equal to 0. Any solutions to that are going to be our eigenvalues. So 2 minus lambda, 4 minus lambda, that's our diagonal. And then the anti-diagonal is going to be minus that 3 times 5 equals 0. So it looks like we get lambda squared minus 6 lambda plus 8 minus 15 is equal to 0. So it looks like we get lambda squared minus 6 lambda minus 7 equals 0. And we could factor that. That looks like lambda minus 7, lambda plus 1 equals 0. So we get lambda equals 7, lambda equals minus 1, and both of these are multiplicity 1 here. Now remember, if all of your eigenvalues are multiplicity 1, it is automatically going to be non-defective. And that is because one of the theorems we proved in chapter 7 is that eigenvectors that come from distinct eigenvalues are always linearly independent. So we know that there's going to be a linearly independent eigenvector for lambda equals 7. We know there's going to be an eigenvector for lambda equals -1. And we know that the eigenvector from here and the eigenvector from here are guaranteed to be linearly independent because they're from different eigenvalues. The trouble happens, the chance for being defective happens when you have a multiplicity higher than 1. But in this case, it should be all good. Now that we have these eigenvalues, we need to go ahead and find the corresponding eigenvectors. So we'll go ahead and do that on our sort of next page here. So now find eigenvectors. So remember our matrix A in this case was, what do we have there? 2, 5, 3, 4. So 2, 5, 3, 4. All right, let's start with lambda equals 7. So how do we do this? Well, remember, we subdue A minus lambda I as our coefficient matrix, and then we solve the corresponding homogeneous system. So we'll subtract 7 off the diagonal, so minus 5, 5, and then 3 minus 3, and then we'll augment with 0, 0, and we'll need to solve that. Should be pretty easy to do so. We can do minus 1/5 R1, and we can do, say, 1/3 R2. So it looks like we should get 1 minus 1, 0, and then 1 minus 1, 0 there. And then we can just take R2 and replace it with R2 minus R1. And looks like we should get 1 minus 1, 0, 0, 0, 0, which makes sense. We're going to get one free parameter, which is because this is a multiplicity 1 eigenvalue, so its eigenspace has to be one-dimensional. It has to have one linearly independent eigenvector. What does it actually look like? Well, if we sort of think about, it's probably dangerous to call them x1 and x2 here because we already have that sort of notation. So you might want to use like a different sort of variable here. So I'll just call them a, I guess, for convenience. We can say that a1 minus a2 is supposed to be 0. Before we do that, we should go ahead and just do our parameterization. We know we want to avoid parameterizing here. So let's just go ahead and let a2 equal to, probably want to avoid t as well since we were using that. So let's let a2 equal r here. So a1 minus a2 equals 0, then becomes a1 minus r equals 0. So a1 is equal to r. So the eigenvectors for lambda equals 7 are of the form RR, which would be, if we want to choose one, we could use as a basis just 1, 1. All right, we only need one linearly independent eigenvector to build our solution, so we might as well just use the one where the parameter is equal to 1. So 1, 1. All right, now with lambda equals minus 1. So we subtract -1, so we add 1 on the diagonal. So we should get 3, 5, 3, 5, 0, 0. And then, of course, we can go ahead and just use this guy directly to clear out the row below. So let's take R2 and replace it with R2 minus R1. So 3, 5, 0, and then 0, 0, 0, 0. All right, we will want to avoid parameterizing this 3. So we can let, we want to switch back to our other column. We can let A2 equal to R, and then we get the equation 3A1 minus 5A2 is equal to 0. So that looks like 3A1 is equal to 5R, and A1 is 5/3 R. Oh, this is a plus here, excuse me. So that should be minus, and that should be minus as well. So there we go, minus 5/3 R. So that tells us that the eigenvectors for lambda equals minus 1 are going to be of the form 5/3 R and R. And so a potential minus 5/3, keep forgetting that. A potential basis would be something like minus 5/3, 1. Could you use something else? Yeah, if you really don't like that fraction, you could say let R be, say, 3. Then we'd say like -5, 3 as a basis, right? I mean, any choice of that parameter R is going to give us one eigenvector, and any one eigenvector here is going to be linearly independent, so we're all good there. Okay, so what does this tell us our general solution looks like? So this tells us that our general solution should be of the form C1E. The first lambda we had was 7, so it should be 7t. And then a representative eigenvalue or eigenvector for that eigenvalue is 1, 1. And then plus C2 e to the -t, that's our second eigenvalue. And a representative eigenvector for that eigenvalue we chose as -5/3, 1. So there we go. There's our solution. Could you format it another way? Sure, you could put all this together so that it just sits as a single vector function, something like c1 e to the 7t minus 5/3 c2 e to the negative t would be the first element, and the second element would be c1 e to the 7t plus c2 e to the negative t. But this is a totally fine presentation of that. Okay, so this is our sort of first example of going through and solving a non-defective constant coefficient system of linear differential equations. Let's go ahead and take a look at a couple more. All right, we're going to try to find the solution, unique solution, to the following IVP. So we've got this constant coefficient system of differential equations, and we've got this initial condition. Just as always, what we're going to do is we're going to ignore the initial condition for the beginning, figure out the general solution to this, and then figure out the appropriate C1, C2, C3 with this sort of initial condition. So let's start by trying to find the general solution. So we want to find general solution. All right, so let's go ahead and convert this into a matrix, into a vector equation. So x prime of t. Here we would get 2, 1, 1, then 0, 3, 0, and then 0, 0, 3. Since for these equations, there's a lot of ones that don't have a 0 constant there. And then that would be, of course, times x of t. Okay. Now that we know what the constant coefficient matrix looks like, we now need to find the eigenvalues. So find eigenvalues of A. So we'll take the determinant of A minus lambda I, so 2 minus lambda 1, 1, 0, 3 minus lambda 0, and 0, 0, 3 minus lambda. Set that determinant equal to 0. Luckily, this right here is a upper triangular matrix, so the determinant is just the product of the diagonal. So this is 2 minus lambda, 3 minus lambda, 3 minus lambda equals 0. So we should be able to easily see that we have an eigenvalue of 2 with multiplicity 1 and an eigenvalue of 3 with multiplicity 2. So we're a little concerned here because we know that with multiplicities higher than 1, there's the potential to be defective. Doesn't mean that it will be defective. If we can find 2 linearly independent eigenvectors for lambda equals 3, we'll be fine, but we got to be a little concerned here. All right, now let's go ahead and find those eigenvectors. So give ourselves another page here. So eigenvectors. So again, I'll just rewrite our matrix. A, the actual matrix here was 2, 1, 1, 0, 3, 0, 0, 0, 3. So let's start with the one that's going to be, that we're sure that it's going to work out nicely, lambda equals 2. So for lambda equals 2, we'll subtract 2 off the diagonal. So 1, 1, 1, or sorry, 0. That was not a good job of subtracting 2 there. 0, 1, 1, 0, 1, 0, and 0, 0, 1. And then we'll augment with 0, 0, 0 and solve that. Okay, doing so shouldn't be too bad. We can use this guy to clear this out right there. So let's go ahead and do row 2 and replace it with row 2 minus row 1. So 0, 1, 1, 0. And then when we do that, we'll get 0, 0, minus 1, 0. And 0, 0, 1, 0. And then we can use this guy to clear this out. So we can take row 3 and replace row 3 with row 3 plus row 2. And it looks like we should get 0, 1, 1, 0. 0, 0, minus 1, 0, 0, 0, 0, 0. Okay, we want to avoid parameterizing this guy and this guy. So we'll actually be parameterizing this guy in front. So we'll let, again, we'll use that notation of A1 equal R. Then we can take this equation here and that tells us that negative A3 is supposed to be 0. So it looks like A3 is 0. And then we'll take this guy up here. That'll be that A2 plus A3 is 0. That tells us that A2 plus 0 is 0. So A2 equals 0 as well. So our A1 is free and the other guys must be 0 here. So eigenvectors are of form R0, 0. And a basis for that then would just be the single eigenvector 1, 0, 0. Could we choose other ones? Sure, as long as it's of this form, right? Since it's only a one-dimensional eigenspace here, just as long as we choose any one of them other than 0, 0, 0, we'll be all good, right? 0, 0, 0 would not be considered an eigenvector here, right? It's part of the eigenspace, but it's not an eigenvector here. So we want to make sure that we use something that's non-zero. All right, I think we have enough space to do the other one. Yeah, so let's go ahead and do for the other eigenvalue, which was 3. So let's go ahead and do that. So for lambda equals 3, we'll go ahead and subtract 3 off the diagonal. So it looks like we should get minus 1, 1, 1. And then otherwise it'll be 0, 0, 0, 0, 0, 0, and we'll augment with 0, 0, 0. And we'll try to solve that guy. So in this case, we want to avoid parameterizing here, but we will actually parameterize twice. And we should be very happy about that, because since we're going to be parameterizing both A2 and A3, that means the eigenspace is going to be two-dimensional, which means that there are going to be two linearly independent eigenvectors, which means that the number of linearly independent eigenvectors matches the multiplicity. So things will be non-defective. Everything's going to work nicely here. So let's go ahead and let A2 equal R, and we'll let A3 equal S. So this top equation then says that negative A1 plus A2 plus A3 is supposed to be 0. So that looks like we could get that we would get R plus S is equal to A1. So we would have eigenvectors of form looks like R plus S, R, and S. So there we go. So what's a basis here? Well, a basis would involve two things. Let's let R be 1, so 1, 1, 0. And then let's let S be 1, 1, 0, 1. So there we go. There's our basis for the eigenspace for lambda equals 3. Now we can put all this together and actually get our general solution. So our general solution here is going to be x of t equals C1e. First lambda that we got was 2. So we'd have e to the 2t times the representative eigenvector for that eigenvalue, which was 1, 0, 0, plus C2 e to the 3t. And we can choose either one, doesn't matter the order here. So we'll just use our first basis element, 1, 1, 0. And then plus C3 e to the 3t, 1, 0, 1. So there we go. There's our general solution. There's two components that involve that e to the 3t because that lambda equals 3 was multiplicity 2, and we just put one with each linearly independent eigenvector. All right, now technically that's the general solution, but we wanted to go a step further. We actually wanted to solve and find the unique solution to the IVP where x1 at 0 is 1, x2 at 0 is 0, and x3 at 0 is negative 1. So let's go a step further and actually rewrite this general solution as a single, rather than broken up into these pieces, as a single vector function. So I'm going to do this on the sort of next page here. Okay, let's copy that. Let's put that one more page. Okay, so we've got this. So let's rewrite this as x of t. And if we look at this, it looks like it's going to be C1 e to the 2t plus C2 e to the 3t plus C3 e to the 3t. And then in the second component, we're just going to get C2 e to the 3t. And then in the third component, we're just going to get C3 e to the 3t. So there we go. That's what this guy would look like as a vector function. Obviously, I could just scoot these guys over here, but just to keep everything sort of nicely aligned. Okay, so now we know that when we plug in at 0, we're supposed to get 1, 0, negative 1. So let's plug in to 0 here. X of 0 is supposed to be 1, 0, negative 1. That was our initial condition here, right? 1, 0, negative 1. Okay. So what is x of 0? Well, let's plug in 0 into this, and it looks like we should get C1 plus C2 plus C3, C2 and C3 is supposed to be 1, 0, minus 1. So what does this tell us then? Well, I guess we can immediately get that C3 is supposed to be negative 1. C2 is supposed to be 0. And if C3 is negative 1, C2 is 0, I think we can just do this in our head. C1 needs to be 2. So C1 is 2. So our unique solution then is x of t equals, well, looks like it would be 2e to the 2t minus e to the 3t, 0, I guess we don't have to write anything more than that, 0, and then negative e to the 3t. There we go. That would be our unique solution there that would satisfy this initial condition and the differential equation. So there's our unique solution. Notice that our unique solution is a vector function. It's 2e to the 2t minus e to the 3t, 0, negative e to the 3t. Okay, let's take a look at just one more example, making sure we're comfortable using this approach for non-defective constant coefficient systems. All right, so this guy it's going to be a little bit larger just to make sure we're comfortable with this. So we're going to try to find the general solution to x prime of t equals axt, with A being this giant, 5 by 5 constant coefficient matrix. So we can jump right in and go ahead and get our eigenvalues. So eigenvalues of A. Hopefully at this point we've done several of these, so you might be able to already spot what the eigenvalues are going to be, especially since this is upper triangular, but we'll go ahead and write it out. It's going to be the determinant of 3 minus lambda, 0, 0, 2 minus 1, 0, 3 minus lambda, 1, 0, 1, 0, 0, 4 minus lambda, 0, 0, 0, 0, 0, 4 minus lambda, 0, and 0, 0, 0, 0, 4 minus lambda. The determinant of that equal to 0. Since it is upper triangular, right, we're just going to go ahead and look at the diagonal to determine the determinant. So it'll become 3 minus lambda squared, 4 minus lambda cubed equals 0. So we get lambda equals 3 with multiplicity 2, and lambda equals 4 with multiplicity 3. So again, there are some concerns here. We have higher multiplicities, so there is the potential that things could maybe could be defective, but we'll go ahead and see what happens. So let's give ourselves another page here, and we'll go ahead and find the eigenvectors. So again, let's remember that A here, what do we have? A was, you know what we'll do is we'll actually bring along the actual page so we can just see this. So we can actually see our matrix here. So first one we have is eigenvectors for lambda equals 3. So let's subtract 3 off the diagonal and augment with the homogeneous system. So 0, 0, 0, 2 minus 1, 0, 0, 1, 0, 1, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 0, 1. And augment that with 0, 0, 0, 0, 0. All right, almost in nice sort of row echelon form, but we're probably going to have to use this guy to clear this stuff out there. So let's go ahead and start that. So let's do R2 and replace, R3, and replace R3 with R3 minus, we can actually do it the other way, which will make it a little bit easier. Let's take R2 and replace it with R2 minus R3. It'll be a little more clever. 0, 0, 0, 2 minus 1, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, and 0, 0, 0, 1, 0, and 0, 0, 0, 0, 1. And then we've got those things augmented there. Okay, this guy looks to be our first position, so we might want to slide him up to the top. It also looks like it might be convenient if this guy was moved here. So let's do a couple interchanges. Let's interchange R1 and R3. And let's also interchange, I guess, R2 and R4. So if we do that, we should have 0, 0, 1, 0, 0. And then instead of R2, we are going to have R4. So we're going to have 0, 0, 0, 1, 0. Then we're going to have R1, so 0, 0, 0, 2 minus 1. And then we'll have R2, which was 0, 0, 0, 0, 1. And then we'll have the original R5, 0, 0, 0, 1. And of course, all that stuff is just 0, 0, 0. Okay, things are looking a little bit better. Now we can take this guy and clear out this right here. We can also use this guy to clear out what's below there. So let's go ahead and do that. We take R3 and replace R3 with R3 minus 2R2. And we'll also take R5 and replace R5 with R5 minus R4. So we have 0, 0, 1, 0, 0, and 0. And we have 0, 0, 0, 1, 0, 0. And we have 0, 0, 0. And then we're taking minus 2 times that guy. So it looks like 0, minus 1, 0. And then 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0. All right, we're almost done, right? Sort of messy, but we're almost there, right? We can just take this guy and use this guy to remove what's right there. So we've got one more operation. Looks like we can just take R4 and replace R4 with R4 plus R3. So it looks like we have 0, 0, 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, minus 1, 0, and then 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay. Well, that was good, right? What do we want to avoid parameterizing? Well, these first two, and actually we can see that everything else, because this guy is going to be 1, minus 1, 1, and actually it's actually not just in row echelon form, it's actually in reduced row echelon form, except for that minus 1 there. This is going to come out pretty easy from here. So let's... my apologies, we don't usually use that notation. We use this guy. We want to avoid parameterizing these, so we will parameterize those first two. So we'll let A1 be R, and we'll let A2 be S. And then we can sort of back solve here, but everything's just going to come out as 0. We can see that negative A5 is supposed to be 0, so A5 is 0. We can see that A4 is supposed to be 0. And we can see that A3 is supposed to be 0. So the eigenvectors here have form RS000, and so a basis, nice and simple, would be 1, 0, 0, 0, 0, and 0, 1, 0, 0, 0. Okay, so there we go. This is good so far because this lambda equals 3 that we had, that guy actually had a multiplicity of 2, and we found 2 linearly independent eigenvectors. Let's go ahead and check out what happens for lambda equals 4. So we'll use another page here. So now for lambda equals 4, let's subtract that off the diagonal and then augment with 0. So minus 1, 0, 0, 2 minus 1. 0, minus 1, 1, 0, 1, and then looks like 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, and 0, 0, 0, 0, 0. And then we have 0, 0, 0, 0, 0. Okay, this is great because unlike the previous one, this one's already in row echelon form, so we're all good. We can go ahead and avoid these guys. So we're going to need 3 parameters here, which is great because the multiplicity was 3. So we'll have A3BR, we'll have A4BS, and we'll have A5. I guess, again, we were trying to want to avoid T, so I guess we can call it, I don't know, how about W, right? We haven't used W for a while, so let's do that. Okay, so this equation here tells us that negative A2 plus A3 plus A5 is supposed to be 0. So we get that negative A2 plus R plus W is supposed to be 0. So we get R plus W is supposed to be A2. So we've got A2 there. And then in the top equation, we get that minus A1 plus 2A4 minus A5 is supposed to be 0. Now that tells us that minus A1 plus 2S minus W is supposed to be 0. And that looks like 2S minus W is supposed to be A1. So that tells us that the eigenvectors have form, well, 2S minus W, R plus W, and then RSW. So a basis here is going to have 3 elements. Let's, I guess, let R be 1 first. So 0, 1, 1, 0, 0. Then we can let S be 1. So 2, 0, 0, 1, 0. And then we can let W be 1. And looks like we get minus 1, 1, 0, 0, 1. So there we go. Then we can put all this together and give ourselves our general solution. X of t is going to be C1e. First eigenvalue that we got was 3. First representative eigenvector was 1, 0, 0, 0. So we can say C1e to the 3t, 1, 0, 0, 0, 0, plus C2e to the 3t, 0, 1, 0, 0, 0, plus C3 e to the 2t, because our 4t, excuse me, e to the 4t, then 0, 1, 1, 0, 0, then plus C4 e to the 4t, 2, 0, 0, 1, 0, plus C5 e to the 4t, minus 1, 1, 0, 0, 1. And there we go. Our general solution right there. So if you guys think about it, this is actually pretty impressive so far what we've managed to do. You guys just, in this example here, solved a 5x5 system of differential equations, and we were able to do that. Now, of course, the limitations so far are that we have to have it be constant coefficient, and we have to have it be non-defective. In our next video, we'll talk a little bit more about this non-defective case, specifically what to do when we get complex eigenvalues, and then we'll be ready to do our last section of the class, section 9.5, which solves the issue of what happens when we have a defective coefficient matrix.